All right, hi everyone. Welcome to the first video for section 4.3. Continuing on with our studies of some of the applications of calculus, or also finding out why this stuff we've been learning is important, useful. Okay, so in section 4.3, we'll be talking about maxima and minima. And let's look at something called critical numbers. So here we have a definition of what a critical number is. So let C represents a number, be an interior point on the domain of F. An interior point, when we say that, if it's an interior point in the domain, we're talking about it's some number that's not on the endpoints of a domain. So like, for example, if the domain of some function was, say, the number 2 to 10, not including the 10, well, 2 would not be an interior point in the domain of this function because it's an endpoint. But a number like, say, 5 would be because it's in between those two endpoints. Okay, so that's what we mean when we say interior point. So let C be an interior point in the domain of F. We say that C is a critical point, or a critical number of function F. F prime equals 0, meaning that the derivative value of that number is 0, or F prime of C is undefined. Okay, so we have two different things going on here. Now, I want us to pay attention to that. First of all, the most common way of finding critical numbers is looking where the derivative is equal to 0. But we also have to remember that it can be where the derivative is undefined as well. So that's something to keep in mind. Okay, so let's go ahead and do an example of finding the critical numbers for this function here. So we have this function v of t equals 2t minus 8 to find the critical numbers. So critical numbers have to do with the derivative. So the first thing we should do, take the derivative. So we'll find v prime of t equals, using the power rule, looks like I'll end up with 4t minus 8. And to find a critical number, I need to figure out where that derivative is equal to 0. So I can do that by just taking the derivative there, set it equal to 0. So I have 0 equals 4t minus 8. I believe if I add 8 divided by 4, we get t equals 2 as one of our critical numbers. Okay, so good. Now let's also check that second condition where f prime of c is undefined. And you won't always have one of these. So if we look at this function, or the derivative here, 4t minus 8, is there a number that we could plug in for that would make that undefined? Well, I think in this case that's not possible, right? Because we don't have anything being divided by something. We don't have any square roots. So there's not going to be any number that we can plug in here that will make this undefined. So t equals 2, the only critical number or critical point here. Okay, so here's some practice that you guys will do in a classwork assignment. So I'm going to go over that for right now, but I will again reiterate that critical numbers are also values where the function or the derivative is undefined. So it's not just where it equals 0, but you also have to check where it's undefined. Okay, now one of the big parts of identifying critical numbers is that the derivative at those numbers equals 0. So the question would be, what does it mean for the derivative of a point to be equal to 0, and why would it be useful information for us? So let's first, well, thinking about that function we were just looking at, v prime, or sorry, it was v of t, and we found that v prime of t equals 0 when t equals 2. So what does that mean? Well, all that our equation for identifying or finding the values of derivatives was to identify the slopes of tangent lines. So if we know that the derivative is equal to 0 at a particular point, what do we know about the tangent line at that point? Well, we know that its slope is 0 because the derivative is equal to there. And if the slope of a line is 0, what is that? Or what does the line look like? So if slope is 0, then ... Well, let's think about this. Slope is 0, which means that it rises nothing regardless of how much it runs, which means that we're looking at a horizontal line, right? Okay, so that means the tangent line at a critical point where the derivative equals 0 would be a horizontal line. And why might that be information? Take a look at this animation. You may remember from here in the quarter. Okay, so this one here. So notice I have this red function here, f of x. And let me do this. And then here you see this dotted line is the tangent line. And as I slide the slider, let's see if we can find some points where the tangent line is equal to 0, or the slope of the tangent line is equal to 0. So not here, not here, not here, but right about, let's see, well, let me get to it. Right about there, a little bit off, but right about there, the slope of the tangent line equals 0. And you might notice that that seems to be a significant point on the graph. And if I continue on, not 0, not 0, not 0, but then right about here, we end up with another point where the slope of the tangent line is 0. And what do you notice about those two? Yeah, they seem to be local extrema of the function, right? So that is one of the reasons we care about where the value of the derivative is equal to 0, because it's going to tell us where local extrema happen. Okay, so before we get too deep into that, let's just do about these terms: local max, local minimum, absolute max, absolute min. So first thing I'm going to do is draw a function, and it's going to look something like this. Okay, and let's first of all talk about, in terms of this graph, what do we mean by local max? This is that word local. If you think about locally, it's stuff that's close by you, right? If something is local, it's close by. So local maximum, or maximas, are points on the graph that are higher than all the points around them, right? So as an example, this one right here would be a local maximum, right? And also, hopefully you also see that the slope of the tangent line there would be 0. Okay. Now let's talk about local mins. Well, similar to local maxes, those are going to be points on the graph where the point is lower than all the points around it. So a point like here would be a local min, or a point like here would be a local min. Okay. Now what about an absolute max? Well, as that term absolute implies, it's going to be a term that is much higher than any of the points around it, right? Not much higher than any of the points. It's going to be the highest point on a graph. Now notice this point right here, this local maximum that we identified, is not actually the absolute max on this graph, right? Where does that occur? Looks like that is up here. Similarly, absolute min, well, we've identified two, this one and one, but only one of those is the absolute min, and that would be this one over here on the right, correct? Because it is lower than any point on the graph. Okay? All right, we will continue more with this on the next video. Thank you for watching.